Well, first of all, I'd like to introduce myself. I'm Silvia Pineda-Munoz. I am a postdoc at National Museum of Natural History's Smithsonian Institution, and I'm the postdoc for a research program called the Evolution of Terrestrial Ecosystems. You can check our website if you want. Today I'm going to talk to you about what is exactly the last chapters of my PhD research. But first of all, I'd like to thank all the institutions that have supported my research while doing my PhD and also while my master's and undergrad research. Also, people at the Smithsonian, Macquarie University, Monash University, University of Helsinki, and Institut Català per l'Ecologia and so forth. But I'm going to start and give you guys a little bit of background. I don't like when people start talking and don't tell me why they're doing what they're doing. So I'm going to give you an idea of why I decided to study what I do. So first of all, I wanted to be able to reconstruct how ecosystems were in the past. So after doing some research, I realized that if I wanted to know how the ecosystems were, I should look basically at the trophic relationships. I could look at other things, but trophic relationships would tell me a lot about how ecosystems work. So in fact, what I needed was to find a way to infer diet in the fossil record. So I started looking at that, and all of us work with mammals. The first thing we realized is that mammal dentition is really variable, and there's a lot of different morphologies. So I wanted to approach that, and started looking on dental morphology, and we have this idea, and it's well known that dentitions will evolve towards what we call optimal morphology, and as time goes, animals have got to adapt their dentitions to be perfectly, as optimum as possible to process food items, and that's also going to improve their fitness. So basically, what we have, theoretically, is, let's imagine we have two clades that have diversified long in time, and then we have here the diets, so we have the carnivore, insectivore, herbivore, and here another clade where we have a frugivore species and also another herbivore. We would expect that these clades sharing the same dietary specializations will share also similar dental morphology features. However, how do we test that? I want to find a method that can prove that, but how can we test if that's the case? Actually, ideally, you'd like to have some model representatives of what you're studying, so it's easier to see what's the diet. But what happens when you're working in the fossil record with clades that have been extinct for so long, and we don't have model representatives, like we see here in this phylogenetic tree from 2007. Well, actually, we still can test some things. We have, for example, eutherians and metherians of placentals and mammals that we know that they diverged around late Jurassic, early Cretaceous. So we can actually use them as a test to see whether we can predict diet from morphology and what are the phylogenetic effects of that. So in order to basically, the idea is if we should be able to draw an ecomorphous space where we have the diets, and these marsupials and placentals with the same diets should fit on the same ecomorphous spaces. So I proceed with that. And basically to do that, I collected 134 species of placentals and marsupials and divided their diet into 8 categories that I established in previous research early on my PhD. After doing that, I used micro-CTs, laser scanners, to 3D scan their dentitions. And, well, here's an example of how dentitions look like after we process them with 3D scanners or micro-CTs. And after that, I designed a method that I call MPDMA, which is multi-proxy dental morphology analysis that it's supposed to, the idea was to be able to preferred diet from that morphology. So basically, on the method, what we do is we look at multiple proxies in order to achieve multidimensionality. A few examples of proxies we look at. One is OPCR, orientation patch count. Basically what it does, it looks at the dental complexity of teeth, of dentitions, looking at, so basically it uses teeth as if they were topographic maps, and they look at the orientation of each point on the tooth surface. In a way, the contiguous points with the same orientation form a patch, and the number of patches will be proportional to the number of mechanical tools we have. So basically, for you to have an idea, each color represents a different direction, so we can see the patches being formed here. Another process I look at was what we call the relief index, which is basically the radial three-dimensional surface as opposed to the base area. And in a way, the more steep dentitions will have more surface. And finally, let's look at the slope, which basically measures the steepness of each grade point on the surface. So after mixing them, I perform an analysis in order to see whether there were morphological differences between diet specializations, principal component analysis to observe what actually the ecomorph species were, and also discriminant analysis. Well, in a previous talk I gave once, there was some people who, like on the questions, they were a bit confused with why I was doing a discriminant analysis. So I have here, like, to give an idea of what it does, although it's not exactly the same mechanism of why I do that. Let's imagine that you go on Netflix and you watch Star Wars and Lord of the Rings, and then next time you open the TV, it's likely that Netflix says, hey, why don't you consider like watching Indiana Jones? Because other people who watch this series also wanted to watch Indiana Jones. On the same way, if I love rock climbing, so I use, here. If I go on Amazon and I buy climbing shoes and a chalk bag, it's probably Amazon's going to suggest, hey, you probably need harness, just security things. So basically, how does this work? After spending a lot of time on art, let's imagine, well, most of us who spend a lot of time on art, I can say, hey, I have these animals that eat plants and look like this. I have these other animals that eat insects and look like this. And I have this fossil species that I don't know what it ate, but it looks like this. So it's like that, it tells me, oh, probably it wasn't a herbivore, right? So that's the idea behind what I was doing. So after applying the discriminant analysis, I found out that I was able to, getting each species out of the data set and inferring the diet, I could discriminate 63% of the species correctly. That was high, but it was still not as good as I wanted to. And I knew there was going to be some constraints. But after looking at the misclassifications, I realized that most of them belong to rodents. Rodents were really, messing it up. So I took them off and see what happened. Naturally, it increased a lot. Had 82% of the species were correctly classified in that case. So, also I looked at how the morphospaces look, and the MANOVA told me that there were significantly differences between diets. But also, I could see that herbivory and carnivory were completely well discriminated. Unfortunately, in a PCA, we can't see all the principal components, but basically observing all the components, most of the diets were correctly classified, as opposed to us using just one single variable, let's say just OPCR, when you just have one dimension for classifying, and you have some limitations. Actually, the principal component, the first principal component analysis, basically discriminated between dentitions with high to low complexity, and the second component analysis with more or less steepness on this tooth surface. So it worked really well. Additionally, I wanted to see what were the taxonomic affiliation of the species on the morphospace, and we saw that there was a fair amount of overlap between marsupials and placentals with the same dietary classification. So just during my research, I created this method, but what is the fear of what I've been doing so far? First of all, I would like to know what's going on with rodents, do a bit more of analysis and to understand why they don't follow the same patterns we see in other mammals. But also, I would like, of course, why not? I'm a paleontologist, so I would like to infer the diet of extinct species and see to what extent we can do that using these morphological methods. Finally, I think the most important innovation about the methods, it can be applied to the study of morphological evolution. Actually, we could be able to look at what happens after perturbation events, such as, for example, climate changes, or the mass extinctions, and actually the fossil record gives us a great opportunity to test that. And so, like a little bit of the conclusions, we can see that diet drives the morphology of the morphology towards analogous optima. So we see that marsupials and placentals with the same dietary specializations will fit in the same ecomorphic spaces. However, we should consider phylogenetic constraints because we will have some misclassifications and some limitations because of phylogenetic constraints. And well, I would like to thank, and I think I have time for questions. Not yet, and I don't think I will, because it's getting on really tricky. I don't. So let's keep them out for a while. These primates, but other primates.